Good morning. So this is Martin Suarez again on the first lesson on astrophysics. We're going to start with astrophysics today. We're going to learn some simple things, most of them probably you're familiar with, about stellar quantities. That means understanding a little bit about the stars and what we see when we look at the universe. So for the history of humanity, we have looked at the skies and made these drawings in the skies. Like this is the giant Orion with the arc here shooting an arrow in this direction. So they made these drawings in the sky connecting stars that probably, some of them are not even stars, connecting, I would say, celestial bodies, maybe galaxies, nebulas, stars, that could help us to find a way, right, in the universe. So this is an example of a constellation. So a constellation, it's an arbitrary drawing that is relative to the Earth, right? It means relative to us. It is not true that these stars are close to each other. It is not probably one of these is not even a star. I think this one here, one of these three, is not a star, but it's a nebula. Right? But then you can identify stars that are very, very visible, like Betelgeuse, Aldebaran, giants. These are drawings in space that are relative to us. They have no gravitational attraction between them. They are at distant places. They're not together, right? There is no bonding between them. So that's a constellation, and a nebula, as I said, is different from a constellation because the stars that are inside a nebula, which is a cloud of gas and dust, and there are stars here that are popping out into existence, right? So a nebula is different from a constellation because in this nebula, it's like a nursery of stars. They are more or less of the same age. They are bonded by gravity, right? New stars that are born. So stars are all the time being born, and they live for a certain period of time, and then they evolve and become dust again. Why is it important for us to look at the light that passes through a nebula? We saw that in topic 9, that the light is giving us information about the spectra of absorption, right? That means the atoms that make this nebula are telling us in the early stages of the universe, which is before the galaxies were formed, when the universe was probably, 20 minutes old, 74% is hydrogen, and I think 25% is helium. So these are the oldest atoms in the universe, and most of the universe is made up of these atoms. So this is important information that we get from the stars that confirm the Big Bang theory, in a way, right? So the atoms that are first created are hydrogen atoms. The question could be, well, when, how are these atoms first created? And that would go into particle physics and baryonic matter at the early stage of the universe, right? Once a star is born, the cloud collapses and it becomes massive enough to reach a point where the temperature and pressure of its core are high enough to ignite fusion. So fusion is a process that liberates energy. So the energy coming out from fusion exerts in all directions. This is a 3-dimensional diagram, a certain pressure. And this pressure is coming by the fusion of hydrogen inside these stars. This is what we now know about, why does the sun shine? Because there is a reaction, a fusion. There is a fusion reaction happening inside the core of a star. But also we know that what pulls the matter together is this force of gravity. So there is an inward pressure that we could call gravitational pressure, right? And when the gravitational pressure and the pressure of fusion are in equilibrium, we say the star is in a stable state, probably in the main sequence, right? There is a state in which the star keeps its shape, it doesn't change much. And all this energy is coming out in the form of electromagnetic radiation. But this equilibrium will not last forever. Nothing lasts forever, not even the universe. Bear in mind that. Okay, so what is the first big question? The first big question is how to measure, and I put this between inverted commas, the distance to a star. This is a very big question. Everything we know from stars comes from light that reaches our eyes. There is no way we can send a spaceship to a star and calculate or measure the distance traveled by the spaceship. So to do that, we use what is called stellar parallax. What is parallax? If you place your thumb in front of your eyes, this is your thumb, right? And this is your left eye and right eye. And you close one eye and you look at the wall at the back of the room through one eye, and then you look at the same wall through the other eye. If you know the distance between the eyes, it's very easy, and if you can measure this angle, it's very easy to use simple trigonometry to calculate this distance, right? Or if you want, this distance, or the distance between your eyes and the wall. This simple method is what is used in stellar parallax. The difference here is that instead of closing one eye, we have the Earth here orbiting the Sun here, totally out of scale. The distance between the Earth and the Sun is, let's call it 1 astronomical unit. It is a fundamental unit in a very important unit in astrophysics. What is 1 astronomical unit? Simply the distance between the Earth. So this could be January, and this could be June. 6 months is, so the Earth is traveling around the Sun. I hope you know that. And we're looking at a star that is relatively close compared to a background of stars that seems to be fixed. So by looking at these stars and measuring these angles on 2 different times of a year, we could use tangent of theta equals opposite, which is 1 astronomical unit, over the adjacent, which is the distance that you want to measure to the stars. The adjacent is the distance, right? So we could do this very easily. And that is called stellar parallax, right? So this is a diagram that explains what I've just been trying to say, right? So this angle here and this distance here, right? So what happens if the angle is very small? If the angle is very small, the tangent of rho is equal to the angle rho in radians. That's a very good approximation for angles that are small, and this angle is really small because the distance to the star is huge compared to the distance to the Sun, right? So yeah, we could even go further and say, okay, let's measure the angle instead of measuring. So let me put here the equation. So for using this approximation, we could say that the distance measured in astronomical unit to the star is equal to 1 astronomical unit over the tangent of rho, which is the same as 1 over rho, using that approximation. So this is the equation. If we know the angle, we know the distance in astronomical units. Now, the astronomical unit is a very small distance when we are looking at stars, so we need to look at another unit. And therefore, we're going to define the distance in parsecs. Parsecs is a bigger unit of distance, and is the distance of parallax measured in an angle that is not measured in degrees, but in arc seconds. An arc of a second. So that is a very tiny angle, and that will give you a distance in parsec. For you to have an idea how big this is, 1 parsec is equivalent to 3.26 light years. This is given in the data booklet, right? So the distance of 1 parsec means, let's put 1 here. The distance of 1 parsec means the same distance that light travels at the speed of light, which is 3 times 10 to the 8 meters per second, for a whole year. So 3.26 light years means 3.26 times that distance that light covers in 1 year. It's a huge distance, right? So we have 3 different units or ways of measuring distances. One is the astronomical unit, another one is the parsecs, and the third one is the light year. And it should be very easy to move from one to other. Okay. Now, is the parallax method the only method? No, there are limitations to the parallax method. Mainly because when light comes from a star to the atmosphere, the layers in the atmosphere produce this phenomena effect called refraction. Light bends, changes direction when it changes interfaces. So we see the stars twinkling, right? So if you're measuring angles from Earth, it is very difficult to measure any angle that is greater than probably the maximum angle that we can measure from Earth, considering this effect, is around 0.01 arc seconds. So that means that the maximum distance in parsecs is around 100 parsecs. So that means stars that are up to 100 parsecs means stars that are pretty close to us, 326 light years away. That means light from stars coming from 326 for light traveling for 300 years. It's not too far away from us, even though it's a huge distance. Now, if it's a telescope that is placed outside the Earth from orbit, we don't have this effect of refraction. So the telescopes, I think one of those is the Gaia mission. It's a mission that is orbiting since 2015. It's orbiting the Earth. And in this case, we can measure distances that are up to, in parsecs, up to 30,000 parsecs. So that means mainly stars that are inside the Milky Way galaxy. We can see probably all the stars in this galaxy. That means it's a method it's very useful for the stars that are in our galaxy, but not enough also to measure stars on other galaxies, right? Okay. What else do we know? We said that everything we see is light. Light that comes from distant stars, and from that light we are able to, remember the diffraction gratings? We're able to see what kind of wavelength is coming from that light. So if we know the wavelength, then we can discover something about, for example, the temperature of a star. And this law, it's called Wien's law. Wien's law. It is an empirical law. I think he won the Nobel Prize for this. It is a law that comes from data, right? But in a way, it connects the temperature to the wavelength of maximum displacement. Because the light that comes from the stars, they have many wavelengths, but as we saw in topic 9, there is a peak for a certain wavelength. So the law establishes that the maximum lambda multiplied by the temperature is equal to a constant. And then that constant is measured experimentally, is 2.90 times 10 to the minus 3, and the unit has to be meters Kelvin, so that when this goes down. So in a way, this law is very useful because we look at the star, we look at the maximum peak, we measure this, and then we can determine the temperature. And if we can determine the temperature, we can see what is the class, the spectral class. Like O is a very hot star. It's around 330,000 kelvins. B, 10,000 to 3. Like the sun is a G star. It's around 6,000 Kelvin. This is the temperature of the outer atmosphere because it's the temperature of the gases that are absorbing and emitting radiation from the star, right? Oh, be a fine girl, kiss me. It's a way of remembering. Undo. I don't know. I don't know what happened here. Okay. Can we move on? No. It's a screenshot. Okay. No screenshot. Let's move on. What else? What other equations do we need to know? Okay. Two concepts. The first concept is luminosity, L. And the second concept is apparent brightness, B. Apparent brightness, okay, what is L? L is power. It is the power of a star, and the apparent brightness is the power of the star that we see per unit area. So, luminosity is the output power of a star measured in watts, and this is like the intensity of a star measured in watts per square meter. So if you have a star that is emitting light in all directions, right? So this is a sphere of energy coming out from a star. This is a star, right? As we increase the distance to the star, we increase the distance. Let's say that this is the distance 1, we increase it to the double the distance 2, and then triple the distance. The area that this beam of light is enclosing is increasing. So there are two things happening here. On one hand, we see that as the distance increases, the intensity decreases. It's an inverse square law, right? There is less power as you increase the distance. And the area that is affecting this is increasing also with the distance, right? So when you're looking at the B, the intensity, it is the luminosity per unit area that is being received by an observer that is standing at a certain distance, right? So the luminosity is something that we can use and measure. This is measurable. Why? Because we can use telescopes sitting on a certain place, like suppose this is the Earth, and we have a telescope, and the telescope has a charge coupled device, which is like a capacitor of light. So they absorb photons of light and they create an image like our retina does, right? So there is a way of measuring the amount of intensity that is the power per unit area. That is B. Power per unit area, right? The apparent brightness is what we actually perceive of the light that reaches us from the star. So again, this is the star, this is a light that reaches us at a certain distance. So we know that the intensity of light is decreasing with an inverse square law, but this is something that we can measure, right? So, and if we know the distance to the star and we know the brightness, then we can calculate the output of the star. That means that power or the energy that is coming out of a star per second. So this is the two concepts that we use a lot in astrophysics. And then we have seen Stefan Boltzmanns' law for black body radiation in topic 8 very recently, right? It was this law, and we say that the emissivity of a star is 1. So this is Stefan Boltzmanns' law for a star. So if we know the temperature, we also know the power. See, we can know the temperature of a star, we know the size of a star, or if we know the power and the temperature, we can calculate the area of a star, for instance. Yeah? Hence, knowing the luminosity from the apparent brightness and the distance and the surface temperature, it is possible to determine the area. So see, we know the size, we know the temperature, we know the distance, we know the atomic structure, that means the components. Everything we know from a star just by looking at light. This is amazing. How we can use laws to understand things that we can't even touch, or we can't even reach, not even close to it. Okay. And then I shared with you in the presentation some facts. One is we are not considering Pluto a planet anymore, and we see that in the Kuiper belt there are many of these similar bodies to Pluto. They're called planetoids or dwarf planets, and since there are many more, the scientists have decided to just consider only 8 and not 9 planets. What is the Kuiper belt? It's a huge swarming mass of icy objects. They're not totally spherical, and they are all beyond Neptune. Yeah, so ice objects that are orbiting around the Earth, the Sun, the solar system. Sorry, yeah, beyond Neptune. So this is an interesting video to watch to see what is out there beyond Neptune. And the Oort cloud, I think also, I don't know if I shared that with you, but Oort cloud is also a boundary to the solar system. So basically, yeah, the Oort clouds and the comets. Comets also, they orbit the sun, but I mean, what is the difference between a comet and a planet? This is a good visual, and there is a video on this. The Oort cloud is about 5,000 to 100,000 astronomical units away. And the Kuiper belt is here. Icy objects, very similar to the asteroid belts that is between the inner and the outer planets, right? So these are different objects, if you want to call them, around the solar system, right? And there are as many solar systems as stars in the universe, so you can imagine the amount of things that are out there. The comets, like I said, if this is the sun and these are the planets more or less orbiting around the sun, the comets have a different type of orbit around the sun also. This is the sun, right? So a comet it's more elliptical, and it takes a long time to come by the sun. And when it comes by the sun, since they're made of ice, the ice is transformed into vapor. So we see this long tail of these icy objects orbiting in bigger orbits around the sun. What do we need to then checklist? Let's see, what have we learned, or what is important to learn from the first lesson? Distinguish between nebula, star, constellation, planet, comet. Understand the equilibrium in a star, the equilibrium between the outgoing and the inner pressure, between gravity pulling inwards and the radiation gas pushing outwards. Understand the method of stellar parallax and do some problems to solve understand the astronomical unit, the parsec and the light year as distances to measure stars, and then two laws, Wien's law and Stefan Boltzmanns law, two laws that we have used in topic 8. And then the concepts of luminosity, apparent brightness, and the inverse square law between the luminosity and the distance. So that's all. First lesson in physics, astrophysics. Just become familiar with these concepts, practice some exercises from the quizzes, and we'll go back to lesson 2 in a minute.